So thanks for being here. It's amazing to be back after a couple of years of being in Chile. So before I start, I want to acknowledge the Bloom Center for inviting me here to give this talk. And also I want to say thanks to the three co-authors of the work that I'm going to show you today. Eduardo Miranda, who's here, James Bantis, who's around there, and Alan Paulus, who couldn't make it today. So, so why do we need a regional perspective for regional risk? If we look at history, we can ask Eduardo to do that. With a couple of exceptions, key exceptions such as HEC 13 and Jesus, we've been historically interested in minimizing the effects of earthquakes on individual structures. For example, if you go to ASCE 7, they provide a probability of collapse of 1% in 50 years for individual structures, and that's kind of the acceptable probability of collapse that we have now for individual structures. However, unless you live in some place like this, we tend to live in communities, and actually most of the world population live in urban areas today, and these urban areas concentrate a large number of structures, thousands or even millions in some cases, large populations, etc. So here we have a couple of examples. This is Tokyo, the most populated city in the world, which sits next to a subduction zone, one of the most actively seismically active regions of the world. Another example is Mexico City, and another huge city with more than 20 million people, and again, this is located in the middle of a subduction zone, a really active subduction zone. We also have examples here in the U.S., the Los Angeles metropolitan area, here San Francisco. Those are really dense cities in the middle of this complex system of active faults. And also, why not Santiago, the city where I'm from, which is the capital of Chile, where we have, just for you to have an idea, every 14 years we have an earthquake with magnitude 8 or larger. 14, I didn't say 40, it's 14 years. So when we go back a little bit, we can get this quote over here from Professors Carwinkler and Deerline, where they were talking about expanding this notion of seismic risk to a regional perspective, and they say a much broader interpretation of performance is needed to understand how communities will be impacted and recover from devastating earthquakes. If we go back to this seminal document, HEC 306, in the commentary section, not everyone goes there, but if you go there, you will find this discussion about what is the implicit risk what is the risk that is implicitly accepted by a city when you use these provisions that are meant for individual structures. And at the end, they put this, which I'm highlighting here. These results emphasize that the perception of the level of safety achieved by the provisions is different for the owner of a single building, the public officials of a city, or the public officials of a state. So they are basically saying, here we have provisions for individual buildings, but the seismic risk of individual buildings is going to be different than the seismic risk of a whole region. Okay, so in terms of an individual structure, we have the structure sitting there on a side with some given conditions, and we have earthquakes around, and the question is, what is the seismic risk? And then that if we can measure that seismic risk, the question is it acceptable or not? And then, even if it's acceptable, the next question is, can we ensure that the regional risk is also acceptable? And sadly, the answer is no. So that's why we need to move to a regional perspective where we have a lot of buildings, a portfolio of buildings, every building in a different site with different site conditions. They will be correlated probably, and then the earthquakes are going to come. And the question now is, what is the seismic risk of the whole region? When we go to a regional perspective, we have new metrics that we have to use. Here are some examples, but actually there are many, many more. The number of collapsed structures, that's kind of like the first metric that probably one can think of. The number of displaced families, also the total economic loss of the region, which is just the sum of the losses of all the components, all the structures, but also things like the total time to repair and rebuild that we've seen in the last couple of presentations, that it's not just summing up all the times to repair all the buildings, because you can kind of repair many buildings at the same time, depending on the available resources and so on. So this is kind of to show you that it's not as easy as just summing up the metrics on an individual scale. And then when we have these metrics, we can ask questions about them. And we can ask, for example, what is the probability that more than 100 buildings will collapse during the next earthquake? Or what is the probability that the total loss of the region is greater than a certain value? These questions are going to be super useful for different stakeholders now. We'll have stakeholders like city level stakeholders, urban planners, the fire departments, etc. Of course, insurance and reinsurance as well. If you need a real life example, this is the SPUR document where they were. This is more than 10 years ago, and they were already saying, look, we have to avoid having more than 5% of the population displaced after a magnitude 7.2 earthquake in the San Andreas Fault. And this is to avoid, as they say, slow and arduous recovery of the city, right? So this is kind of saying this is the metric that I'm interested in. Once we go to a regional scale, we'll have new challenges and new problems for research, which is actually good for everyone, right? So first, we will need an exposure model. This is where are the structures, what are their characteristics, etc., how it evolves in time. Then we will need also a hazard model that not only accounts for mean and standard deviations of the intensity, but also we will need spatial correlations of intensities at different sites. In terms of vulnerability, we will also need the correlation of structural capacities at different structures. They can share some things that make them weaker or stronger than the average. And on top of this, we'll have a large number of variables, like a really large number of variables. So that means a significant computational effort. So we will also need like efficient methods to do this. So I'm going to show you a little bit of the things that we've been doing and we done a couple of years ago. So in terms of exposure, we developed this pipeline where we take Google Maps images and also real estate information and create these exposure models with machine learning algorithms. And you can see here two examples. One is Napa on the left, the other one is San Carlos on the right. And in those maps, each point is one specific house. And for each house, we can estimate the year of construction and also the number of stories. For the hazard model, we develop a spatial correlation model for intensities. So what we did here was to fit a spatial correlation model to different events, different earthquakes, one by one. And then we observed, as you can see in the image of the right hand, that different events have significantly different spatial correlation models. So there's a lot of variability here between one event and another. And our model, the novelty is that it considers that event-to-event variability, and it propagates that variability into the whole process. For the vulnerability model, we developed this spatial correlation model of structural capacities. This one depends not only on the distance between the structures, but also the difference in their years of construction. So what we are saying here is if two structures are really close and also were constructed in the same era, then probably they will share these things that make them weaker or stronger than the average, and also they will probably be subjected to the same ground motion or pretty similar ground motion. So that's why they are more correlated than others. Then for the number of large number of variables that we have, we developed this efficient framework based on reduced order models that you can see in the bottom are really good at matching the structural response. So this is a framework for evaluating the seismic risk of portfolios of tall buildings, and actually this was part of the dissertation of James Bantis. Once we got to here, we said, okay, let's play with this model, let's play with this framework, and we took the database of tall buildings in San Francisco, and we've made several things, and I'm going to show you just this one, which is where we took only the steel moment frame buildings built before 1989, and we subjected them to the Loma Prieta earthquake to see what are the drift demands on each of the buildings, and also what is the probability of yielding and fracture in the connections. So we can do these cool maps showing those responses. The last thing that I want to talk about is this regional risk target seismic design that we are proposing. This is basically saying, okay, you have a seismic risk on a regional scale, which in this case is the red line over there. This is for San Francisco. It's just an example. And we, for example, are interested in the probability of having more than 20,000 units lost due to collapse. And that probability over there is around 8%. So the question is, can we increase the design level of our structures to decrease this risk to an acceptable level? And let's say that acceptable level is 1% of probability. But the novelty here is that we are going to increase the seismic design level depending on the density of the region, because denser regions will have more structures subjected to the same ground motions, probably sharing some characteristics that make them stronger or weaker, so those will be correlated. And what happens is that we get maps like this one, where those regions with higher densities of structures will get penalized with higher values. If you think that this is weird, why are we gonna penalize a region because it's just a high density region? We can think about the importance factor that we have in our codes. And I think that we all agree that this is a good idea. What is this idea? So imagine that we have a building with a lot of people inside. The occupancy level is going to be high. So when that happens, the building code says, okay, that's fine, but you have to increase your design level by 25%. Why? Well, because if this building collapses, then the consequences are going to be devastating, right? There's a lot of people there, and it could be a real problem if it collapses. Well, what I'm saying is, if I take that people and put them together in buildings that are similar and that are close by, then again, we have a similar problem. Those buildings, if they feel all the same ground motion, and that ground motion is going to be really high, hopefully not, but if it's really high, and if those buildings share some deficiencies that make them weaker than the average, then most of them are going to collapse simultaneously, and the consequences are going to be devastating. So why not imposing a penalty factor or an importance factor like the one on the other building to all those buildings as well? What we are trying to avoid at the end of the day is this, right? Thank you very much.